no one else was available. There's a chat about, I guess, a loosely mixed together group of projects. seL4 or seL4 verified will be the central one of them. There are a couple of others. It's a big group of people that worked on various things, and I'll mention some of the projects as well. And the essential component of that is the seL4 parser that gives you a semantics for C deeply encoded in Isabelle and the tools that build on that. So obviously, the function of the thing is to give you a model of a C program in Isabelle. One of the annoying limitations is that for the moment, parser.
Can you take your laptop and just sit closer to the?
Yes. Excuse me one sec. I'm going to try and sit closer to the microphone. Audio check. Can everyone hear me fine?
Great notes.
Great notes. Okay, good. That will have to do. Right. So the point of this is to take a C program, give you some semantics in Isabelle, and one of the limitations is that for the moment we can only handle one C file at a time. So, for instance, the seL4 build system has a mechanism for hash including everything into one file for silly reasons. To build a verified build, and then you prove something about it. And in fact, there are now a few different ways of doing that. So we start off, one of the tools we're building on already gives us a verification condition generator in a horse style. There's big step and small step semantics, and there's a fairly manual way of doing a refinement / simulation proof up to another model based on that stitching of those tools. And I'll discuss Dave Greenaway's kind of automated version of that right at the end. And finally, in addition to proving things upwards, proving things that are abstractions of the C program or proving the C program implements certain rules, you can also prove things downwards. So there's some work by me on translation validation to compare against marks. For example, here is the world's second stupidest, ridiculous example I made up, reverse a list and increment all the elements in it. And if we elaborate that into Isabelle, we get something as horrific as that. Just in case no one can read the text, don't even try. Just to point out that, you know, the kinds of things you'd expect from one of these tools have happened. So all of the checks that the C standard does, for instance, when you incremented something by one, it turned into these kind of overcomplicated checks. Certain kinds of sign capitulations don't overflow. Actually, there's quite a lot of constructors in here which is to do with details of how the memory model works. Let's keep running along. The C semantics we're working with is basically a combination of three things: Tetris model and the elaboration we just saw. I made up these slides relatively quickly, and I know I'm going into too much detail, but it's kind of useful, I think, to give some flavor of what this thing is concretely. So Simple comes from a project that was before ours, Verisoft, which is run in Germany. German did a whole bunch of work there on building a simple imperative language. In Isabelle, you can see its constructors at the bottom there, and you can probably guess the operational semantics from the name of the constructors, right? Single steps for skip and conditional and so forth are absolutely straightforward. So that gives us, which is deeply encoded at the statement level, and then sort of forces us to be shallowly encoded at the expression level, which honestly is a little bit of a frustration if we had our time over, but there we go. And then the interesting thing I wanted to talk about a little bit, a bit eccentric, is the memory model we use. So within the global state of this thing, the heap is represented as two objects. So at the bottom there, you have this one-dimensional array of what all the bytes are, which is exactly what you'd expect. It's just literally bytes where they would be. And then there's this representation above that. It's actually two-dimensional that says which point is valid. So I just make the diagram slightly easier to read. And so you have a 4-byte integer pointer. And then At the next level above that, you have aggregate types that include things that are important at level 1. And you can probably guess the pointer is value of all of the representation of things that are in touch.
I'm having a lot of trouble hearing now.
Oh, so I need to stop talking to the other people in the room and stare at this black box.
Probably.
By staring at the screen. So the model directly gives us, notion of whether pointers are valid and how to access and update them. And it's pretty standard to turn this into a partial map here. So you have a lift operation that lifts the heap for any given type up to that. And when you do that, you get for free that operations on one type won't touch another unless one of those types can be a field of the other. And that's, in fact, everything we needed for alpha verified. The obvious question for most people is, what about aliasing within one type? And Harvey, in his PhD, built a separation logic on top of this model, which we didn't actually use in most of the big results. So there you go.
Because
that I'm going to rush past that because it's an interesting question, but the answer is a bit complicated. Essentially, because this is exactly what you want for a refinement to another program that has the same kind of state model, partial maps of blah 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 blah. And until something actually separates, you've got no need for separation logic. So there are a couple of annoying quirks, but essentially the other program is advancing all of the state in the same sense. It's not a composition of programs. If the modules separated in memory, it would all get more interesting. If there was some pair of modules that shared a type but were otherwise separate, it would be useful, etc. Okay, so I went into a little bit of detail about this because there's some people on this call who have worked with systems that are quite different. Note that there's no direct equivalent of provenance in this model, which confuses people. This is, however, not the kind of portable assembler model that I've appealed to before. Absolutely, there are types and there's a notion of which one is valid and whatnot, and we can say more about this. Right, so one of the consequences of this is the model can't exactly be sound against the C standard as the standard is written. However, the translation validation happens to work with a few packs built in. So there's an interesting observation. Okay, the parser does what you expect. Like Kevin Merrin, whose kind of work is fed into the CN project here, Michael spent a bunch of time during his PhD thinking about exactly how to formalize the C standard, and he worked on this gadget that parses C into this fully explicit version and some eccentric features about it. Right, so we're able to treat local variables as local because you're not allowed to take the addresses of them. So we don't need to worry about the fact they're accessed both as heap values and as regular L values. And in fact, there are some hacks to do the same kinds of things with global variables. So if their addresses,
quieter again.
So if their addresses are never taken, we treat them either as constants or as variables. And all of this is to kind of simplify hand reasoning and simplify the kinds of proofs that are painful at times. For instance, in early versions of BST, you probably get what's going on there. At the cost of making the translation validation more complicated. Right. Some things that we never addressed. Simple, when I was using it, was intrinsically single-threaded. There is this proposed replacement. Simple without an E becomes complex without an E, which is going to be concurrent and blah, 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 blah. I don't know whatever happened to that. And likewise, I left the group 5 years ago. I also don't know about other stuff that's been going on in Isabel, apparently. And finally, I'll show you in a demo in a sec. Autocorrers is this gadget for doing the same kind of conversion of, correspondence between a monadic representation and a C representation that we did by hand in the alpha verified project. In this case, the monadic program gets synthesized rather than handwritten. So if I switch here, go there, show you the file. there is exactly the same C program I wrote. I showed on the slide, just a couple of steps. This is the process of running C parser. Has to define a bunch of standard theorems for all types. And then run autocorrers, file, run, sit there, and go. It's doing span definitions. So there is the elaborated. So there is the elaborated deep encoding. Here is the simplified shallow encoding, which is derived from that. And if I switch over, I had about enough time between when this meeting started and now to define a proof in a silly style that this is valid with a couple of cheats. I'm not going to go into the details. So here's the question I'd ask you all. What questions would you like me to answer about it, other than what I've shown you already? We have 0 minutes for that.
Okay, thank you. People should ask him that question.
It's hard for me to see what's going on in Zoom.
Yeah, you should just stop presenting.
There is
At the top.
Right.
Few options.
And people are only talking about the sound. Cool.
Okay, questions?
So there's no separation logic in the system. You mentioned that there was some separation logic, but you don't end up using it. Is that right?
Right. So the model defines what point of validity means. And on top of that, we have a naive way of reasoning about the whole heap of objects of one type. And there is also a separation logic for that. The separation logic was not particularly useful for the L4 verified proof because of the way that it's done. And
So if I understand right, correct me when it's not, it's basically because the upwards proof is a whole system simulation of.
right. So for starters, separation logic to define the state relation. We didn't need to, and we didn't clearly get much benefit from it. And I will admit that I didn't understand separation logic well at the time at which we were doing that, but maybe Golan did, so details. But we also struggled to find places in which we could clearly separate one thing from another. And again, I've already gone into enough detail, but without going into more detail, it's a bit hard to explain exactly why.
Makes sense.
Well, right, sorry, but one of the things that I was sort of trying to clarify here is that the model gives you a whole bunch of choices how to reason about this thing, whether to first convert it to a simplified monad or to do the same proof explicitly on deep embedding, how to talk about the state. So the state is just a parameter that gets passed around, but you then have a choice what operations to use on that, etc. So yes, you could definitely use Harvey's separation logic setup, and he expected that we would. And in the hour since I started writing that demo code, I haven't done any of that because I literally don't remember how. Yeah. Michael.
Yes. So that looks very interesting. But one thing I'm always struggling a bit with, like the seL4 stuff, is like just figuring out, learning more about that or figuring out how it works. Like, do you have some references or some recommendations for figuring out how seL4 or like in general the verification toolchain there works, and like what should I look at if I want to understand that better?
Yeah, that's a good that's a good question. Let me just ask the same question back to you in different words though. What kinds of questions do you want to answer about it? I mean,
Yeah, for example, like
right. Or one of the equivalents.
right, yeah, like like just the first question is like there seem to be many tools. Like there's, I don't know, there's the main seL4 repo, there's autochorus, there's some of these other parsers or so. Like, which one, like, do you think and it's not clear like which is kind of the current state, which is maybe some project, but it's not maybe what's going on, or
I mean, seL4 and Alpha Verified were always two different repositories. They have slightly different history, but there is a single thing somewhere that uses Google Repo, I think it is, which is not an amazing tool, but it will do for this job to check out everything you need. And then there's effectively a single makefile that runs everything. So if you just want to see it wasting your CPU time, then you can do that. And that should get you the current state of mainline.
okay, and you meant like should that be linked from the main seL4 side or something like that, or okay. Actually haven't checked in a while. Well, I don't know, maybe we can also do this offline. Well, but like just kind of what would be the canonical getting started materials or so for learning about more about this tool chain.
Don't have a good answer, and that's almost a personal failure, because one of my jobs, which I never did 5 or 6 years ago, was meant to be to try and write some kind of tutorial material for new people joining the team. And we never came up with good examples.
Have there been any summer schools or anything?
No, not like that.
So something that would be nice, but it's maybe too much work for anyone to do, would be, well, you say that the tooling, it can be used in different ways, but maybe the sort of the seL4 verification architecture is one of the most interesting such ways. So if one had the tiniest example, but with that refinement to a higher level model proof.
This is always the complication, that the easiest for any medium-sized model, for any medium-sized problem. And certainly for a small problem, it just looks silly.
Yeah.
Right. Step one, create a copy of it.
This is why I want to focus in this whole endeavor on the most instructive examples, not the line counts of the examples.
So, yeah, I don't have a good answer to this question. If you can steal the time of any of the many people who've worked on this project before, we can take you on a tour of bits of the repository. But if you want to do things by hand, the standard solution is to pick off one of the patches that the implementation team are furiously building, and try and rerun the proofs. And
Andrew had a question.
Are the C verification tools in connection with the seL4 verification currently in use for other projects besides the maintenance of the seL4 proof? Does it have users outside of the sort of core seL4 group?
So I put too much on those slides. There are a handful of things, but none of them particularly big. So the autochorus gadget that Dave Greenaway built makes that encoded C representation look less scary. And that turns out to have been very attractive to consumers. So Christine Riscala, while she was still at MPI in Germany, did some proofs about some graph algorithms based on that, and the Cogent project builds on it. But the Cogent project was, again, mostly an Australian project. People now moving around.
And is Cogent still an active thing?
I don't really know. I know, so Christine joined that project, and I know she's still working on it. But since
I had
Darby
a
moved
postdoc
up
who just
here.
joined me, and he was working on it right before.
Right, exactly.
There's now another thing based on Cogent called Dargent, which is like some data format thing, kind of like Kathleen Fisher was doing back in the 90s. But now in a proof assistant.
I don't know is the good answer to the question. I mean, it's sometimes called the L4 verified C framework, but there's no particular reason that it needs to be used for seL4 only. But there are only modestly many other consumers ever, and I'm not sure if any of them are still working on it.
I guess the point of my question is, if there were some benchmark suite that, this group of people somehow jointly created, is it likely that people will be from the L4 verified C tool project will be, demonstrating the use of that tool on benchmark suite?
Yeah, who would we put in charge of being responsible for that? I'm not sure. I still know how to annoy Michael and get him to do things. But...
Yeah. All right, that was my question.
Okay, Abhishek, have you got a quick question?
So you mentioned that the proof is like a whole system refinement. So I was wondering whether you investigated ways to decompose that refinement proof from the model to C into smaller either refinement subproofs or things like that. And if so, what was your experience?
Well, the whole puzzle with that kind of problem is giving a structure to the decomposition. In that case, the next up level of the model shares many of the same function names as the C program. They just calculations they're doing. So the proof of abstraction or the proof of refinement is a mix of actually proving things about the encoding and just matching up the syntax of the programs as they step through doing similar things. And then as you proceed further up the abstraction chain, the program becomes less abstract, it becomes less complex and more abstract that way. Without drawing diagrams or wasting even more time, I don't have a good way to kind of explain the different kinds of decomposition there, but yes, there are substantial. But it's most separation in the syntax of the various programs rather than by concept